Good afternoon, everyone. We are Group 11 and our thesis project is about security in IoT networks. Throughout the presentation, we will give you an overview of our work over the past 2 semesters. We will talk about the security issues that we tackled in IoT networks, and we will be explaining our results and our contribution to the topic, as well explain our system design and show a short demo of our work, and finally walk you through the project outcome. Now, I will be presenting an overview of our project that started at the beginning of this academic year. Milestone 1. At the beginning of Thesis 1, we decided to study the attacks on cyber physical systems and of the most dangerous attack, and this included physical, SCADA, smart meter, and network-based attacks. And our plan at this time was to introduce the following solution: a software solution which was building a security layer over the TCP IP, and a hardware solution which is implementing a system on a chip into the smart meter. Following, we moved to our second milestone. And during this time, we had to take a decision regarding which attack will we continue working on. And after many research, we picked data injection attacks, as they were the closest option to our aim of securing IoT networks. And our proposed solution became more clear, in which we decided to build a 4-layer security protocol and implement a system on a chip on the smart meter. Moving on, we came to milestone 3, which was at the end of Thesis 1 to the beginning of Thesis 2. Our aim now was to get more focused and start the on-ground work after all the research we've done, which led to a number of decisions. The first decision is that we decided to concentrate on distributed denial of services attacks for 2 reasons. The first, they were the most dangerous attacks that faced the smart grids. And second, it was not feasible to cover all the data injection attacks in the remaining time. The second decision is that we decided that we will not continue on our hardware solution, as we faced a lot of obstacles to get the smart meter and also access its design to start working on it. The third decision is that we started looking for data sets to implement our simulation. And fourth, we decided to start looking for a simulation tool and start working on it. And the tool that we found at this time was known as Nour. Given that, we moved to our solution, which was building a 4-layer security protocol and simulating it using the datasets. Finally, we reached milestone 4, which represents our work till this day. As we worked on implementing the security layer of our protocol, we decided to work on 2 layers instead of 4. And we wanted to finish on time and achieve some positive results. We also decided to not continue working with Snort, as it wasn't suitable for our purpose and was not easily adjusted so that it matches our security protocol. Therefore, we built our customized simulator. Last but not least, after studying the datasets and implementing them, we decided to widen our targeted attacks, as the process of detecting DDoS attacks was the same for other attacks, such as DOS, renaissance, and theft. Therefore, our protocol can detect now more attacks. So the 2 layers of our security protocol are prevention, which was implementing a public key encryption using elliptic curve cryptography. Second layer was detection, which was using machine learning to detect smart attacks and smart grids. Reaching to our end results, which is a research paper about security of IoT networks that includes a summary of all the information we gathered and analyzed about the topic from research, and a simulation of our 2-layer security protocol that is implemented using the data from the real smart grids datasets.
Okay, so going into tackling the issue of security in IoT networks, our main aim is to solve the vulnerability problems of the IoT-constrained devices in the network, as IoT devices are naturally vulnerable to security attacks, so with all of its benefits, such a point should not be neglected. So we have 3 main motivations behind this aim. First of all, there has been an increase in the rate of attacks on IoT devices in the past several years. An article showed that the number of attacks has increased by 600%, from around 6,000 attacks in 2016 to almost 50,000 attacks in 2017, which is definitely a really huge increase in 1 year only. One other thing, that it is a continuously growing industry where the market is expected to grow from $52.3 billion in 2018 to $141.2 billion in 2023, with around a 22% increase per year. This is, of course, a notable increase, and given the really high number of increasing attacks, such a point should definitely be tackled. Finally, one other thing is that IoT has a unique nature and requirements for its devices. They are less computationally powerful and more susceptible to attacks, as hackers can gain access to the devices through the remote access and control from the internet or through the availability of weak passwords.
So before we start with our solution for the issue of security in IoT networks, we needed to survey the available literature and see what has been achieved and where we can take it a step further. Although there are numerous publications covering this topic, we will present a subset of them that cover the main conclusions or ideas. We first looked at literature that covered intrusion detection systems in general. We found an overwhelming set of publications that show that machine learning-based anomaly detection systems outperform the traditional signature-based ones. For example, in the first two papers, titled Performance Evaluation of Supervised Machine Learning Models and Evaluation of Machine Learning Algorithms for Intrusion Detection Systems, it was concluded that the random forest classifier outperformed shallow models and even multi-layer perceptrons, or the MLP classifier. On the other hand, in a paper published in the Applied Sciences Journal, they concluded that deep learning models outperform shallow models, but are more computationally expensive. We can conclude from these contradicting conclusions that the random forest classifier and neural networks stood out as potentially good models to use in intrusion detection systems. We then moved on to look at papers that covered intrusion detection systems specifically in IoT networks to guide our work more effectively. In a paper titled Intrusion Detection Systems for IoT-Based Smart Environments, they stated that machine learning-based anomaly detection models are a promising technique in intrusion detection systems. Also, in another paper, they showed that machine learning-based models outperform the signature-based ones in IoT environments. Finally, in a paper titled Threat Analysis of IoT Networks Using Artificial Neural Networks, they achieved a 99.4% accuracy with a neural network-based system, but they only tested it on a dataset with distributed denial of service attacks. With those paper and many others in mind, our aim became to expand on all of this previous work and build an intrusion detection system better suited for the IoT environment by taking the nature of the constrained devices in mind, and that covers more than one attack, while exploring new approaches such as ensemble learning and federated architecture.
Okay, so going into our system design, we have used a machine learning approach to the detection part of our intrusion detection system. It consisted of a three-step process. The first step was data collection, cleaning, and feature generation, where we worked on finding a suitable data set to use, removing any redundant data, and working on feature generation by choosing the most correlated feature. Then the second step was surveying different models in terms of accuracy, precision, and recall. The models we looked at are logistic regression, random forest classifiers, and multi-layer perceptron. As in the related work, some stated that random forest classifiers are better, while others stated that neural networks are much better. For example, the paper that gave an accuracy of 99.4% used neural networks, but tested only on one attack. Therefore, even though our main focus was not surveying the different models, we decided to try these two models given our data set and the different attacks we were testing on, as we wanted to continue with the best model while moving forward. As for logistic regression, it was used as a benchmark for the other two models since it's a simple one to implement. So we wanted to see how the two other models compare to it. Finally, the third step was choosing the best model and implementing the final structure. From the survey done, we saw that the best model to use is the random forest classifier according to the accuracy levels and the F1 score, which can be defined as a weighted average of the precision and recall, where the precision shows the number of true positives over the sum of true positives and false positives. In this case, false positives can be defined as when we predict that there is an attack, but there is no attack. However, recall is the number of positives over the sum of true positives and false negatives, where false negative is when we predict there is no attack, but there is one. And as seen from the diagram here, random forest classifiers had the highest numbers for both metrics.
So why does the random forest classifier work so well? One reason is because it's based on a concept called ensemble learning. Simply, this is a method of learning based on using several models on a body of data to hone in the best features of each model. It ultimately relies on the fact that each model will have different weak points that will then be compensated for by the other models. In the case of a random forest classifier, what happens is that we have several instances of decision trees, and each will be fed a random subset of instances with a random subset of features that they will then use to build each tree. A testing instance will be fed to all decision trees, each of which will output its prediction, and votes, or the average, will be taken to decide on the class of the instance. So as we see in the diagram, each classifier will output its prediction, the result will be averaged out, and the final prediction will be based on that. Moving on to the architecture for the network, we propose the use of a federated architecture, but before we talk about why we chose it, we will discuss what exactly is a federated architecture and how it's different from what most systems are based on. Let's start with what's in use now, which is the centralized architecture. We first start on the left with a 4-node architecture with a central node, or CN in this case, and edge nodes named EN, and which are considered the constrained IoT devices. The first step is that data is moved from the edge nodes to the central node. The central node will then train using the received data and produce the final model with specific weights. These weights are then sent back to the edge nodes. These edge nodes will then use these weights to predict whether the new incoming packets are malicious or not. In contrast, in the federated architecture, each node uses its locally stored data to train and build its model and generate unique weights. These weights are then sent to the central node, which will average them out and sends them back to the edge nodes, which use them for the final weights to do their prediction. We can see that the federated architecture is fundamentally different, but is still superior, because by allowing the data in each edge node to stay locally in that node and not be sent to the network, the data is now more secure and will not be under the risk of attack while being transferred throughout the network. A second advantage to using the federated architecture is that it allows for less network congestion, since instead of sending huge amounts of data through the network, we will only be transferring weights. Although each node will have to train its own model, it is still computationally feasible.
We have decided for Network Simulator 3 to be the link for our entire research study. It allowed us to validate our findings and profile how the entire framework operates as a whole. This was done by implementing the Akari topology, integrating each component of our project into its respective layers, adding standards on which Akari operates like Sigma CA, time synchronization, etc. And finally, making use of all of the above to create a test bench on which we will validate our findings. The Akari topology follows the following structure. Smart meters are connected through a star topology to a PAN coordinator that governs the whole communication process and links each cell to the IP backbone indirectly. Each PAN coordinator forms a cell, and each cell is capable of intercommunication through their respective PAN coordinators. Each group of cells is considered a cluster and are assigned to a cluster coordinator that acts as a single point of communication between the whole network and the IP backbone, linking to the SCADA system. The whole network is referred to as a cluster workshop, where the workshops are defined by the cluster coordinator controlling it and the clusters connected to it. This video shows the first phase of the simulation where the nodes are created and the topology logic is applied. The node at the top left is the workshop coordinator, while the blue ones are the PAN coordinators. The remaining nodes are smart meters in the area. The simulation starts by showing the workshop coordinator sending a wake-up synchronized signal The simulation starts by showing the workshop coordinator sending a wake-up signal to the last recognized PAN coordinator for a given cluster. The PAN coordinator then sends a synchronized broadcast to all nodes in the area, and the second PAN receives it as well. Contention begins, and data is transmitted back and forth between PANs to determine which coordinator will handle the cluster, based on time taken to receive and send data to nodes. In other words, based on distance. Once a PAN coordinator has taken control of a cluster, the connected nodes' addresses are gathered by the PAN coordinator and sent back to the workshop coordinator for control. So far, we have discussed how everything was built and for what purpose, but how are they all linked together? When the simulation starts, nodes are created, each given a role, an IP address, and a subnet mask. The machine learning model is loaded into each of the nodes' memory for execution. The PAN coordinator initiates connection with all nodes in its vicinity, and public key exchange begins to verify authenticity. This is the part illustrated in the demonstration video. The simulation can now begin, and data begins to flow through the network. Rogue nodes begin various denial of service attempts to a random target node, either through a vulnerable IP backbone or through vulnerable clusters. To divide this train of handling predictions, each node is responsible for processing the data it receives. If an attack is detected, the tuple of flagged IPs is sent to the PAN coordinator, which blocks any traffic from those IPs. While all this is running, performance metrics are logged by calculating various timestamps between operations to get a rough estimate on how much processing power was consumed by each node, along with a data dump in PCAP format for post-processing. The structure of the network contains 7 workshops with 2,500 PAN coordinators per workshop. Each PAN coordinator is assigned to 15 end nodes for a total of 262,500 nodes. The attack simulation was done by dynamically allocating 3,000 nodes near a certain cluster and randomly attacking either the coordinator or a specific node in the cluster. The simulation was kept running for a total of 3 days. From the PCAP file, we are able to retrieve downtime for attack nodes as well as getting durations for sleep-wake cycles of each node. From the PCAP file, we are able to retrieve downtime for attack nodes as well as getting durations for sleep-wake cycles of each node for energy calculation. The main metric for validation in our experiment was downtime, as it denotes not only that the model did not predict an attack, but also the time taken for recuperation to take place, and for the node to reboot and connect to the cluster. Our data showed that we have up to 0.329% average downtime, which in other words is a 28-hour downtime duration per year. Finally, as a side project, we have also taken interest in modeling power consumption of the network in general. This was done through getting the timestamps for cycles mentioned earlier, along with specifications from smart meter providers available for the public. Most smart meters available in the market feature a direct AC power supply, and hence limited energy does not pose an issue. However, in volatile areas like smart meters for gas pricing, a battery is often used to reduce the risk of electrical fires. Most common battery capacities are around the range of 16 ampere hours, which is enough to run a smart meter for approximately 12 years before requiring maintenance. Due to the higher computational power needed by the prediction model and the encryption scheme, energy consumption was bound to increase, but with optimizations. The new expected lifetime of meters following this framework is around 9 years, which is a very acceptable lifetime considering that the IoT industry is a relatively new field and the energy issue is heavily invested in to improve sustainability. We have to mention that several limitations existed in our research that may impose different results. The PAN coordinator, for example, consumed exceptionally more power than all other devices due to the fact that it's still receiving the packets from the attacking devices. Connection rejection in itself is demanding as the node is able to sleep for much shorter periods. A mitigation technique may prove very useful if PANs in the future were to run on a limited power source. Also, simulating attacks in NS3 is not a 100% realistic decision, as a multitude of variables exist in the real world, along with various types of denial of service that could be attempted. Although through our dataset, we trained the model to be capable of detecting most software-based denial of service attacks, the simulation limits us to what we can validate. With that being said, testing can be conducted on physical networks, but this is beyond our capabilities at the moment.
Okay, our project is divided into 3 main parts: detection, encryption, and simulation. For the detection, even though we included 4 different types of attacks in our model, we got a really high accuracy of 99.8%, which is very high compared to other papers. This shows how well the detection part works in our project. Our encryption is done using elliptic curve cryptography, which is built based on a paper that can be found in the references. It also has a very simple structure. Finally, we also managed to implement our own protocol on the simulator and test using it. In conclusion, we came up with a contribution to the literature by how machine learning-based intrusion detection systems can be built and the idea of adding security as a service. We have all the backup research that is needed for this to become a product. Our project can also be sold as a security as a service for both detection and prevention, as they are both working well. For the further works in federated learning, we need to remodel the OCARI protocol to include a time period dedicated to weight transfer. Secondly, for cryptography, we were trying to improve the scheme that we found in a paper, but we were not able to resolve the issue of securing the first message. Finally, we did not have the time to implement our architecture on an actual physical network. That's it. Thank you.